Hello, everyone. Welcome to the 2025 PIBBSS Symposium. Our speaker, Callum Lawson, will be talking about evolutionary game theory and its connection to reinforcement learning.
Nice. Thanks, Callum. Yeah, so this is some work I'm doing for PIBBSS Fellowship. Been working with Michael Dennis, looking at, evolutionary game theory, reinforcement learning, and focused around this thing of like adaptive environments. So this whole talk's going to be about environments that adapt to what the agent's doing and kind of change the problem setting. And this has been like a massive part of the like capabilities research with like self-play, producing these superhuman AIs in terms of like game playing. And it's also becoming part of this whole like agentic LLMs thing of like getting agents to browse the web, maybe interact with each other. You see this in San Francisco, like there's just these billboards absolutely everywhere about like agent software, agent activities. And so that's also a problem where the agent is encountering an environment that is changing depending on what the agent's doing. And this is all like part of a general thing of the sort of problem setting of machine learning and AI, like changing from only, not only, but being the focus being on like supervised learning on fixed data sets to agents that go and gather their own data. And so there's this kind of feedback loop between the environment that they're and the data that they're gathering. And so like, for instance, with those agents on like gathering web data, they might go encounter some websites, take that data back, simulate, generate synthetic data. There's these kind of like environments, and the data they're training on is adapting to what the agent's doing. And so I'm really interested in robustness stuff to do with this kind of problem setting. I really like this paper. This is like illustrating the problem where there's this superhuman Go AI, this Kata Go AI, which like could be any human kind of just heads up. But then if you, despite it being like superhuman in capabilities, it can still be exploited. There's still weak points. So you can train an agent to find what the weak points in the strategy are. And in this case, it was like this big encirclement strategy, which you never normally see apparently in Go games. But humans can emulate this strategy and then beat this superhuman AI. So the point being that even AIs with very that are very capable in general have these kind of failure modes, and that's something that can happen even with very like simple agents and simple environments. You can also get like not only these kind of robustness failures, but also like goal misgeneralization, where the agent has learned something in training which was not really the intention. So this is an example from Karim Abdel-Sadek, who did this paper on goal misgeneralization, where you have an agent that's, in this case, a mouse trying to find the cheese. But in training, the cheese is always in the top left corner, or it's always on a plate. And so it can't disambiguate those two things in training. And it ends up, when you put it into a different environment than it's seen in training, then it will start like going for the left corner or going for the plate rather than going for the cheese. And so they're both cases where you have these like failure modes of the AIs because of things they've seen in training. And that's like a general thing that I'm interested in terms of this. Like in most of RL, the objective is to maximize your expected reward across the environments that you see in training. And that means that you care about the environments you see most in training, and you don't know how to deal with environments that you see rarely or not at all. And so like this is just an example from a model we'll see later, but where you've got a bunch of different maze designs, and there's particular ones that look more similar. These 16 rooms ones look like the ones it's seen in training, and so it's very good on those, but the ones it hasn't seen in training, it performs very poorly on. And so that's because it's really maximizing the average of its performance of the stuff that it sees in training. And then, so my supervisor, Michael Dennis, and a bunch of other people have been looking into these algorithms that I think are really cool. They're like these unsupervised environment design algorithms. So this is again in the problem setting of like adaptive environments where the environment's changing training based on what the agent's doing. But in this case, it's really trying to show the agent environments that it's where it's having these failure cases. So it's trying to really like seek out those problem cases in training and show them to the agent so that it's kind of robust to a wider range of environments. And there's a bunch of different ways of doing that, which I think are quite cool. So they're all acronyms, but like DR is domain randomization. So that's going to be like the base case. This is where you have no algorithm for selecting environments. You just show some like random distribution. So maybe like a random distribution of mazes, which are more like random blocks scattered on a grid, basically. And then there's a couple of different versions of these unsupervised environment design algorithms. So one is paired, which is the one Michael developed, which this has like a student that's learning to try and achieve a task, like maybe find its way out of a maze, and an environment generator, this is sort of like a GAN setup where it's an adversarial game, and the generator has to try and generate mazes that are hard for the student to solve. And so they're kind of in a kind of arms race against each other. And again, that leads to the generator like seeking out the failure modes of the student and trying to show it those kinds of mazes that it's not doing well on. There's another one which I think was developed kind of semi-independently called PLR, Prioritized Level Replay. It's quite similar to Prioritized Experience Replay, if you know that from reinforcement learning. But basically the idea there is to have, rather than an environment generator, you have a kind of buffer that you sample environments from. And you keep around and sample preferentially from the environments where the agent's got more to learn or where it's struggling more. So kind of doing the same thing, except from like a sampling thing rather than a generation thing. And then Excel is more or less the current state of the art approach to this problem, which is like kind of a mix of both. So it's a sampling one, it's got a buffer of levels, but instead of the new levels in that being randomly generated, they're like mutated from the current ones that are problematic for the agent, so you make small changes. And as I say, that one's kind of the one that seems to be best at the moment at getting the agent to be like robust across different environments. There are a few other approaches recently which have performed similarly, but and this is just an example again from Karim's paper, so this kind of mouse cheese setup again, and when he uses like Excel or PLR, these algorithms that seek out the result of that paper is that these algorithms are able to find there's very few levels to start with where the cheese is in a different place to the top left corner or to the plate. But it seeks those out and it starts showing them a lot to the agent. And so it's then in training, it's able to understand that it's supposed to be going for the goal, supposed to be going for the cheese, not for the plate or for the top left corner. And then, so basically these algorithms, I think are really exciting because they're a potential way to kind of scale, kind of aligned training of agents. So where you're trying to make robust agents, two cases where you've got these really like the kinds of approaches that people have used for the like capabilities research, where you have like try and train really like superhuman game players, and as I say, with agents becoming more and more of a thing, LLM agents. The thing I'm excited about these algorithms is that they offer a way, because they're automated algorithms, they're not like human tailored training programs. That's potentially, if they work well, if they produce robust agents, then they're a really good way to scale that to really complex training and try and like push that training towards areas where you're getting robust aligned agents rather than something else. And I think one thing with that is that it's similar to GANs and other methods where you have these kind of adversarial arms race things. The training process can go down different trajectories and you don't always end up with a robust agent at the end. And so I'm interested in trying to use approaches to understand that feedback, that adaptive environments training process, and like figure out like how can we set those algorithms up so that it takes us to a space where we want to, robust, aligned kind of agents. And my background's in ecology evolution, so one thing that kind of struck me about this is it felt kind of like these unsupervised environment design algorithms felt kind of like a feedback process that you see in evolutionary game theory. And there's a lot of predictions from evolutionary game theory which we'll go into, but I'm just interested in this as potentially one way to kind of understand these training dynamics where you've got these environment feedbacks. And so like the kind of loose analogy to the evolutionary game theory case is when you've got like, say you've got like a species that has some policy, some strategy for gathering food, and it might be like very good at gathering one type of food. And then you have a feedback from the environment that like reduces the reward that it's getting from, because that food source will go down, it will be getting less food from that source, and there's an incentive to kind of broaden out and be able to exploit other food resources and perform in other kinds of environments apart from the one that's kind of very well exploited or populated at the moment. So there's a kind of similar process where you have this environment feedback, which is pushing you to be good across a broader range of things than, well, potentially there's different outcomes that can happen, which we'll come to. And yeah, just to say there's like a couple of different ways you can think about this analogy. So one is to kind of have the classic unsupervised environment design setup that we were just talking about, where, like for instance, in those mazes we were looking at, like where the algorithm is adapting the mazes that it's showing, there isn't a direct interaction between agents in that case. It's just individual agents going through a maze, but there's a kind of feedback between agents and policy, like the policies of the agents and the environments, because the agent's changing its policy and the environment's updating, and then the environment distribution is updating, and it's kind of a feedback like that. But the agents aren't, it's a multi-agent problem in the sense of like the optimization algorithm, but it's not the like episode itself, the problem setting itself doesn't involve direct interactions between agents. And you could extend to that case as well, like have like evolutionary game theory is also good at those kinds of things of like cooperation and competition directly between agents in an RL episode. But for the moment, I'm just focusing on this case where it's the arms race is between your agent policy and your environment, rather than like a problem setting where competition or cooperation is important. I just wanted to say a little bit about the theory why I think this would be cool to try and like make this link between evolutionary game theory and these unsupervised environment design algorithms. One prediction, I think basically the evolutionary theory could be useful for understanding when, like how robustness is achieved and whether that's achieved through like diversity, generalization, different like strategies that can evolve to deal with, like in the case of evolution, this is like a variable environments problem where you don't know exactly which environment you're going to encounter, and you have to be evolving to deal with different scenarios that can arise, and that distribution can change. And so one prediction, for example, is the importance of trade-offs in that setting. So you have some settings where it's like depending on the problem, the trade-off between the environments is concave, and that means in that case it's better to be a generalist that's just pretty good in both. So you're one policy that's just decent at dealing with both environments. And then there's other cases where you have like convex trade-offs, where in fact the best strategy is to do different things, to have a mix of things that you do. It's like a mixed strategy that can arise in different ways, which we'll see in a second. But I just think this is interesting because if this link could be made, then you could look at how the trade-offs of your particular problem setting would lead to generalization or specialization of agents. And then to sort of drill down on that diversity specialization point, there's actually two ways that you can have diversity in policies arising in the evolutionary game theory sense. One is to have a single policy which randomizes. So it's just a mixed strategy in the sense it's like picking, or if it's a continuous case, it's picking over some distribution of actions that it could take with like probability. And I think this is evolutionary bet hedging in evolutionary literature. I think it's equivalent to like a stochastic policy in reinforcement learning. Then the other case would be, in that case, it's just a single replicating thing, which is just changing what it does. The other case you could have would be a population of agents where you have different things coexisting and specializing on particular parts of the environment. So I think that would be interesting for like the population-based training or the explicitly multi-agent reinforcement learning case where agents are actually interacting. And what's really cool with that is like there's a bunch of theory for how that diversity in agents can arise from you start with a single type of agent, you do the training, and eventually they split. Like basically the fitness landscape is shifting underneath the agent. So rather than it just being a fixed like optimization problem where you just need to find one best solution, the agent is changing its policy, and the fitness landscape, the environment, like the rewards that you're getting are changing as it moves, depending on how it moves across that landscape. And the branching that you get happens when you get a species evolving to it sort of hill climbs to a point where the landscape then splits, and it kind of splits it into two different species. There's selection pressure to do different things, which I find really cool. And an example of that is with this like an empirical example is with these Galapagos finches, where you have like initially you have like some distribution of seeds. This is like a distribution of seed. Well, shown is a distribution of beak sizes, but you would have in the environment would be some distribution of seed sizes. And then like you start off with a type that's kind of good at some intermediate size that's common. And then because of this feedback thing with the environment, that then depletes those seed sizes in the environment, and you get selection pressure for speciation, where you have different species that are then specializing on larger and smaller seeds, which are now more common than they were before. So that's why I think the theory is cool, why I think it would be interesting, why it might offer some kind of predictions for the sorts of dynamics you might get with these adaptive training algorithms. Now I'm going to try and focus on, so I'm not going to like test those predictions today. I'm just going to try and develop the initial overlap between the analogy between evolutionary game theory and these unsupervised environment design algorithms as like a starting point to try and figure that stuff out and make predictions. And so I do think there are some quite strong, when I looked into these algorithms, I do think there are some quite strong similarities between how unsupervised environment design works and how these evolutionary game theory specifically works. So this is another thing. It's also slightly different to evolutionary algorithms, which are often ways of exploring. They're often, not always, but often applied to fixed optimization problems, and they're ways of kind of combining strategies to have new strategies that might be better at solving the problem. This is like a different kind of, both are evolution inspired, but evolutionary algorithms are different to evolutionary game theory in this sense, because evolutionary game theory is very much about this feedback that you get from the environment, and this kind of change in the problem as you get better at it. And so in evolutionary game theory, you have selection gradients, which are basically the way the technique works is you start with some policy, you start with some strategy in a particular environment. You then mutate it, you try something that's like similar but slightly different. And then you see in the environment that's determined by your current policy, does this new one have a positive growth rate against it? In other words, like can it replace, like multiply itself at more than replacement rate in the population that's currently dominated by the first strategy? In evolutionary game theory, these are called like resident and invaders. You have your resident, which is your current policy. You have your invader, which is your like a policy update, if you like, and you're seeing, can the invader improve on the rewards or fitness gained by the resident. But the key is that it's relative to the resident. So your interest is in making gains against specifically this current policy. And so I think this selection gradient is pretty similar to a policy gradient, where you have like a current policy and you try a small update and you see if it improves the reward that you get. Although the reward functions are slightly different. And then you basically iterate that in evolutionary game theory until you get to the evolutionary stable strategy, which is essentially slightly different to a Nash equilibrium. There's an extra condition on it, but it is very similar, very close like analogy. It's basically a Nash equilibrium with an extra condition, which we could go into if we wanted. But and this is like an example from a simple environment model, but I think it's more general. Which is saying the condition for the evolutionary stable strategy. And what we're looking at here is like, so P here is the strategy, P star is the equilibrium evolutionary stable strategy, P is like an invader that you're trying. So you're trying a new strategy against the old one. R is like the rewards or fitness that you get. And F is the distribution. So S is a particular environment and F is the distribution of environments. So this is basically saying a strategy is in this setting where you have a fluctuating environment is an evolutionary stable or equilibrium strategy if for all the possible mutations you could do, the possible updates you could do, none of them would have a positive growth rate against the current one. As in, if you take the ratio of their fitnesses and you take an expectation of that over the possible environments that they could encounter, that needs to be less than 1 for all the possible invaders. So there's no, it's like, that's the Nash equilibrium sense of like, there's no change in strategy you could make which would improve your utility, if you like. And this is kind of where this differs a little bit from some like more traditional like RL approaches, is this fact that it's not only the environments, the frequency of the different environments that you're encountering that matters, it's also how well is the current thing that you're comparing to doing in those. And so you can think of that as kind of like how populated is this particular environment. Like if the current strategy is doing very well in a given environment, so maybe like it's like a given seat size, then you've got an incentive to do better in environments that are currently like underpopulated relative to that. And this is like referred to in ecology as like an ideal free distribution. The analogy is to like ducks in a pond, where you would have like bread that you've some bread source in the pond. There's like a high density of resource in some sense in some part of the pond, but you as a duck you can do well by either going to that high reward zone or by going to a lower reward zone where nobody else is currently doing stuff, if that makes sense. And this is kind of like the idea with this this kind of relative fitness. This is called a reproductive, like expected reproductive value. It's like the thing that matters is your fitness relative to others, your like the current incumbent strategy. Were you going to ask a question?
Yeah, so I wanted to ask if we're assuming there's no specialization, I think the like current strategy is one single strategy as opposed to a portfolio. Like, is that an assumption here?
So the question is whether there's an assumption here about the current strategy being a single strategy rather than a mixed strategy, rather than a portfolio. Is that what you meant? No, that assumption's that this is the R here is the like expected reproductive success, so the expected number of offspring in that generation for that environment, and that can come from a mixed strategy. So it can be a mix of other. The R's here don't have to be pure strategies; they can be mixes of other. You can mix in whatever strategy profiles you want here to get your strategy, if that makes sense. And so portfolios are allowed, basically.
Yeah, just like that. Okay, I can imagine like one strategy being like a probabilistic mixture of other deterministic strategies. And also I can imagine just the population containing two types of different deterministic strategies. And the two.
Okay. Yeah. True. Yeah. Okay.
Like only consider the first type and not the second type. Yeah, just to clarify.
Yeah, so the question is about whether that mix could be a mix over deterministic strategies or also a mix over mixed strategies, basically, right? Mixed over probabilities. I guess does it work out the same though? I don't know, because it's kind of like
yeah, that's like these agents will be like in games with each other, and in that case, it makes sense to have different mixed strategies.
yeah.
Don't know exact same.
Yeah, I mean that's a big. So the comments about like agents potentially being in games against each other and mixed strategies being really important in that context when you're playing, like, I guess you mean like the opposing agent not knowing what you're going to play, right? This is a big part of evolutionary game theory. It's actually not a big part of this model because this is from strategies just growing in a fluctuating environment and there's no direct competition between them. But like the foundations of evolutionary game theory were very much in that kind of behavioral, I'm encountering another individual, what are they going to do? And being predictable would make you exploitable. So like mixed strategies are like a big part of that for sure.
Right.
So we've got these like these kind of 2 points of similarity, the policy gradient selection gradient part, which tells you how you update the policy, and the evolutionary stable strategy, which is like the point you get to, the optimal strategy that you end up at. And what I have been doing is like trying to just do a very like early stage initial modification of the base case algorithm, so domain randomization, this case where you just are randomly showing environments and there's no adaptive feedback, and modifying that algorithm in the smallest possible way to get an evolutionary game theory type model out of it, and then comparing that to the existing unsupervised environment design models and looking for similarities and differences. And so it's all based around this idea of like population, or like you can think of this equation that we just looked at as a like the current reward of the current strategy. Sorry, this is of the new strategy, the invader, being like the benefit it gets there being weighted not only by how often it's seeing different environments, but also by how well the policy that you're updating, the current policy, is doing. And so the approaches are all based around that idea where you have a weighting of the importance of environments, the importance of rollouts from particular environments, by how well you're currently doing, like how well the current policy is doing in those environments. And we're doing this with a softmax function where, so G here is the return, so the total cumulative reward. And so it's actually a soft min, so we're doing like essentially an weighting of the inverse of how well the current policy is doing, and we downweight or upweight environments according to that function. And we do that in a couple of ways. I think this is actually quite cool. There's 2 ways which are in some sense equivalent, but actually result in different training dynamics. So one is to just directly weight the policy gradient. So you can sample a bunch of random environments, and then you can say, okay, we've got actions and rewards from those environments, but we're going to upweight actions from the environments where the current policy is doing poorly in that gradient that we're doing. So you're like weighting the gradient inversely to how well it's currently doing. So difficult environments become more important in the policy gradient and policy update. And we also put that into the it should probably say a bit about the algorithm. So this is kind of a bread and butter reinforcement learning algorithm, PPA. And it works by having two networks, policy network, which determines what your strategy is given the states, what your actions are, and a value network, which is like the critic, which tells you or tries to estimate how good certain actions are going to be. But I guess the main thing to know is that this is like a standard algorithm that's also used in a lot of the unsupervised environment design approaches. And then there's a second way of doing it, which is rather than sampling environments randomly and then weighting the kind of underpopulated environments in the policy gradient update, you can also do a kind of sampling version where you show environments according to how hard they are. And so like you preferentially show the environments where the agent's currently performing most poorly. So that's more of like the first is a modification of this domain randomization algorithm. The second is a modification of one of the existing unsupervised environment design algorithms, this prioritized level replay algorithm. I don't know how am I doing for time here. Okay, cool. So the RL setting that we've been doing this in is just this kind of classic maze design case. So you've got an agent trying to solve a maze, and you've got the environment distribution is the distribution of possible mazes that you could be shown. And so we do, I won't go into all the training details, but I mean, basically this is 10 seeds of our training program. And these are, the performance is, so the algorithms decide which mazes to show in training, and then we evaluate all of them on the same set of evaluation mazes, which are these 8 more structured mazes than they actually see. So the mazes that they actually see in training are often like sprinklings of blocks. They're not particularly, they gather structure over time as the algorithm proceeds, depending on the algorithm. But these actually do look quite different to the kinds of things they're seeing in training. And so it's a measure of like how robust are they when you put them into a setting they haven't seen before. And so there's a bunch of algorithms plotted here, but it's basically the two evolutionary approaches we just talked about versus the 3 kind of benchmark approaches from one of the earlier slides. So I mean, this is the basic benchmark domain randomization, random environments. This is the normal prioritized level replay algorithm. And this is Excel. This is the one that did some sampling and some mutation of the levels as well. And that's the current kind of, or close to current state of the art. So what was kind of surprising is that this evolutionary game theory analogy algorithm actually performed with this set of hyperparameters, we'll come to that in a second, performed like equivalently essentially to this Excel algorithm. And so this at least says that we're capturing, by doing this like upweighting of environments where the agent's performing poorly, we are doing something like this idea of these other algorithms, which are kind of selecting environments that are hard for the agent and kind of upweighting those when they show the agent those environments. So I guess the main thing from this, this feels like the training dynamics are at least comparable to Excel. Yeah.
I'm not sure, but it feels like the upweighting then is like calculating regrets, as in like the difference between your reward versus the optimal reward, except that the optimal here is effectively like invading policy.
I mean, let's come to that later, because that's where I want to go next with the so the question was about whether this upweighting is similar to a regret-based measure, and that is actually the next like thing I want to get onto with the research. So let's come back to that a bit later on. So thanks. Yeah, and just to show the performance, the different algorithms on different mazes, basically there's a couple of mazes that they all do well on, which are these 16 rooms mazes, which look more like the mazes that they see in training, because I mean, they are structured, but they're less obviously structured than the other like evaluation mazes. So all the algorithms do pretty well on these, especially this one here. But the main thing is that particularly Excel and the evolutionary ones seem like they have higher performance on mazes that are less like the ones that they've seen in training. So they're in a sense more robust in the sense of being able to still achieve their goal in a maze which looks different to the mazes they commonly see in training. So again, that kind of suggests that these evolutionary things are doing something similar in training to the unsupervised environment design algorithms, or at least to Excel. One interesting thing was that actually, when you look at the correlations in performance by run, Excel stands out as quite different to the other algorithms, and so the actual performance on a given runs, it still seems that Excel is doing something different to these to all the other algorithms in terms of the way the agent's behaving. And this is just another view on the sort of robustness side of things in some sense. This is the performance plots, but now scaled relative to the best performance for that particular algorithm. So we're now taking out how good the algorithm actually is on a given maze and are looking at how evenly does it perform on different mazes. And again, it's kind of like the evolutionary ones. Well, particularly the domain randomization one seems to be more even than without the evolutionary modification, and a little bit the same case with the evolutionary one of PLR. So it does suggest that that evolutionary thing of upweighting the environments where you're doing poorly does lead to a more robust policy. And then in terms of so where we would want to go with this in terms of understanding the sorts of policies that are arising, the first step would be to quantify the trade-offs between the different environments, because that's what the evolutionary theory, that's kind of the input that it takes. And that was quite tricky. So I mean, basically, when you look at correlations in performance between the different mazes across all algorithms, I mean, you pretty much pick up this distinction between these two mazes, what they do really well on, all the algorithms do pretty well on, which look more like the ones they saw in training, and the performance across the mazes that look a bit more different to the ones they see in training. But there wasn't an obvious, I was expecting more of like a trade-off between, just based on the idea that there are different algorithms for searching mazes, and some are going to be better on, there's going to be a trade-off in how well a given algorithm performs on one maze versus another, just because of if you're doing like depth first search versus breadth first search, that's going to work better on some mazes than others. Even simple things like whether you prefer to turn left or right, like that's going to create some sort of trade-off. And we're not really seeing those in the performance on the different mazes. And we think this is probably because these algorithms have, I mean, we've run them for a number of updates, which is like comparable to the ones that are in the literature, but I think they probably haven't converged to like an optimal policy in some sense. And so they haven't got to the point where the trade-offs are the key determinant of whether they do well or badly on a particular maze. So the hard constraints of trade-offs aren't the key factor here. Then this is all about me learning about finickiness of RL. We noticed that the performance of Excel in particular seemed to be a bit less than, so it was similar to, this is all, by the way, based on this JAX UED package, which is really good. So like we've used a lot of their code, so thanks to the authors for writing that. We were getting similar performance to the runs in the paper associated with that package, but not to the actual original papers published for these algorithms. And so we decided to do a check for especially effective learning rates on the performance of the different algorithms. And it seems to make a massive difference. You can get domain randomization coming out on top, like for certain learning rates. I mean, these are not this learning rate sweep is not for huge, like a lot of these are just one seed. So this is like very noisy. Some of the ones in the center here are for more, but I guess the only clear thing I could see here is that different algorithms are the peak performance of the algorithm seems to be learning rate dependent, and different learning rates are better for different algorithms. And also that for some reason, the evolutionary version of domain randomization seems to be slightly less sensitive to learning rates. I'm not sure why that is, but it might be an interesting thing to look at. I think in the evolutionary game theory framework, learning rates would be similar to like a mutation rate. It's like how big a step you're taking. So kind of curious to look into that. But yeah, basically to say, although these evolutionary algorithms are clearly in some ways doing something similar to unsupervised environment design, and so there's some analogy there. And then there might be some transferability applicability of predictions from the evolutionary models to unsupervised environment design. The details are going to matter, and particularly the hyperparameters. It does look like they're quite important. Now we come on to the thing about regret. So I'd be curious to chat to you in detail about this actually, but the analogy is incomplete at the moment because these unsupervised environment design algorithms are based on regret-based performance. And one reason that that's really important is like these are mazes generated, for example, by our evolutionary algorithm, the sampling one, and they're very highly prioritized in the environment buffer because the agent is performing very poorly on them. It's because the goal is literally walled off from the agent and it can't get to it. So it always gets a terrible score. And this is like a problem with the algorithm because there is no robustness that can be gained from these mazes. Like it's just unsolvable, but the algorithm is really, really like prioritizing it. And regret gets around that problem because regret is the measure of your performance, the performance you left on the table, essentially, that your performance relative to how well you could have done, often it's tricky to calculate, but to some measure of optimal solution for that maze. And so a regret-based measure, like the PED algorithm, for example, it depends how well it can estimate the regret, but if you knew the regret, it would get around this problem because you would say, well, the agent's doing as well as it can, which is like, it can never get there. Like that's, there's no point in showing this level. This is not like a resource to be gained, you know, to get fitness from. This is just like a useless level, basically. And so, yeah, I think maybe it's a good thing to have a detailed chat about afterwards, actually, but I'd be interested, like this is the immediate next step is, this is one thing that's missing from the evolutionary things that we've been doing. We've got a thing which upweights difficult environments, but we haven't got a thing that says the environments are too difficult and you're not going to learn from it. So that's like something we want to build in. And then what we'd like to do is really move into the predictions part, like the evolutionary theory predictions part, which is like specifically around mechanisms of robustness, like how under different trade-off settings you get different, like robustness is achieved in different ways, generalization versus specialization, for example, or this thing we talked about earlier of specialization in the sense of mixing between specialized strategies as stochastic policy, or having multiple policies in a population that do different things. And for that, we would need to extend to the population-based training type approach, which is something I'm quite keen to do. So yeah, just to try and draw things together. I mean, basically, I'd be excited about using evolutionary game theory to try and figure out how we've set up these in unsupervised environment design algorithms to take us to places that we want to go, to robust, aligned policies. I do think there's a lot that evolutionary theory could add here in terms of like what we were just talking about, the kinds of mechanisms of robustness that you get. At least the initial work I think that I've been doing with this PIBBSS fellowship has like, I was kind of surprised at some of like how similar some of the things were, how similar like selection gradients and policy gradients seem to be. This idea of resource competition being analogous to this thing of like pushing the algorithm into environments that it's not currently doing well at. And it is possible to build an algorithm, at least as a first pass. Like it's definitely not going to be the final analogy, but it's like, it's capturing something about how unsupervised environment design algorithms are achieving this robustness. So there's some useful similarities there, I guess. And then, yeah, as I say, the two things I want to immediately want to get into this regret thing, like trying to figure out how to make that analogy even tighter, and then actually bringing in the theory and seeing if it predicts the kinds of strategies that you would get, especially in a population-based setting. So yeah, with that, I'll finish. Just wanted to say thanks very much to PIBBSS. It's been like the best summer, honestly. I've had such a good time. I really enjoyed being in San Francisco. It's been super, like, it's just been fantastic working with Michael. Like, I've learned a ton. I just had a great time. So yeah, thank you very much for providing that experience. Thanks.
Okay, do we have any final questions from the audience?
I guess maybe we can go to the room here first, just to see. I don't know if anyone had any questions. If not,
so quite a basic question, I guess. But I see that you're trying to make the link between these sorts of experiments you're doing in conditioning, game theory, and robustness and alignment. I see the link with robustness, but with alignment, I think it's a little more tricky to make.
Yeah.
Because, like, how do we differentiate between robustly capable agents and robustly aligned?
Yes.
Like there's some formulations that try to study it, like perhaps like misalignment is not the same as incapability, but it's like the systems or agents that we're studying seem to still be very capably optimizing for some goal. It's just not like the goal that we're.
Yeah, right.
How do we formalize that, and how can we actually study it in this sort of thing?
Yeah. So the questions around the link to robustness being clear, but the link to alignment being less so, and potentially more difficult. I mean, I agree. I definitely agree that to me the robustness stuff is pretty close to like the generalization stuff, which is like, so there's like that kind of dual use stuff of like capabilities on the generalization side versus like an algorithm that does not. It's basically, in both cases, you're interested in an algorithm that does something according to how you define the rewards, which is like, I guess with alignment, it's often when if you have misalignment, it's when your rewards specification is an imperfect description of what you actually would like, how you would actually like the agent to behave. I do think that Kareem's stuff on the goal misgeneralization stuff is in that direction, in the sense of like you're looking at whether the algorithm can do the thing you want it to, whether the mouse can retrieve the cheese, which is what you want it to do, not go into the top left corner, which is what it thought it had to do based on the reward. But I definitely agree. I also kind of, alignment just feels more tricky to define from the evolutionary point of view. I guess maybe it would come up more in like the multi-agent settings where you have cooperation, things like that. But yeah, I guess I've mostly been focusing on the robustness stuff, but I have to think more about the alignment side and whether evolutionary game theory would have stuff to say about that. I think. Yeah, I have to think. Yeah, that's a good point though. Are there any questions from the online audience?
Okay, if that's all the questions, then we'll end the recording there. Thank you for talking, and then we'll send you to the breakout room.
All right, thanks.